Assalamu alaikum class. Today we'll discuss another lecture of separation processes 1. Today is 24th of March 2025. So the topic of our today's lecture will be adsorption. The topic is based on the chapter number 25 of the unit operations book by McCabe and Smith, which is already shared with you, the whole class. And we'll discuss about the adsorption, its basic concept, its definition, its explanation, types of adsorption, and then principle of adsorption process, and about adsorption equilibrium, and we'll also discuss about the breakthrough curves. So first of all, let us discuss what is adsorption. Adsorption is defined as the phenomenon of attracting and retaining the molecules of a substance on the surface of the liquid or solid, resulting into a higher concentration of that molecules on the surface. It's basically an exothermic process. So if you see, we have this solid A, which is the known as the adsorbent, and adsorbent is defined as basically the substance onto which the new molecules are attached, are adsorbed. Okay. For example, A is the adsorbent. So here A is the adsorbent, which is the basic solid particles, mostly porous particles, and B is the second item, which is basically adsorbed onto that solid surface. Mostly it could be gas, or also it could be liquid, but in our case we will discuss mostly about the gas adsorption. And this B is known as adsorbate. The substance that adsorbed onto the surface is called adsorbate. Here B is adsorbate. Here you can also see another figure. We have unimolecular adsorption and multi-layer adsorption. So a little bit I will discuss about this. In a unimolecular adsorption, you have only one layer of the adsorbate onto the adsorbents, which are attached on with the help of weak van der Waals forces. It's a physical bond, not a chemically reacted substance. It's a physical bond that can also be broken with the help of the steam when we regenerate the entire column. So in the multimolecular layer we have weak van der Waals forces, and the bond is like very weak, and certain molecules also retain on the top. So we have two different types of surface occupying mechanism in this case. So we have two different separation mechanism. One is adsorption, which is starting from AD, and the rest is sorption. And second one is absorption, which we have also discussed in the class. So you can see adsorption is different from the absorption. Here adsorption is the surface phenomena and absorption is bulk phenomena. So there are certain differences here. As you can see in this figure, absorption, the solute molecules or the adsorbate absorbs inside the body of the absorbent, whereas adsorption is the surface phenomena. It retains only on the surface. So concentration of adsorbed molecules are greater at the immediate vicinity of the surface rather than the free phase, whereas absorption involves bulk penetration through diffusion processes. Absorption, on the other hand, adsorption is a rapid process and happens quickly, whereas absorption, the equilibrium takes very slowly. So reverse of adsorption is desorption. Adsorption reverse is desorption. So here you can see an interesting figure here, where we have this shows the adsorption, which is surface phenomena, and here it's going inside the body and is the absorption. So types of adsorption, we have basically two types of adsorption. We have physical adsorption and we have chemical adsorption. Physical adsorption is the only bonding is the weak van der Waals forces There is no significant redistribution of electron density in either the molecule or at the substrate's surface. And whereas the chemical adsorption, we have a chemical bond involving substantial rearrangement of electron density is formed between the adsorbate and the adsorbent. The nature of this bond may lie anywhere between the extremes of the virtuality, complete ionic or complete covalent character. So just I will explain that we have two types of adsorption. Physical adsorption. In physical adsorption, the adsorbate molecules only retain on the adsorbents, and that can also be reversed. Whereas in the chemical adsorption, there is a chemical bond being formed between the two species, adsorbent, adsorbate, and it cannot be reversed. Mostly we will focus on physical adsorption, because chemical adsorption is basically a chemical reaction, and a whole adsorbent band needs to be replaced in that case. So let us see differences between the physical adsorption and chemical adsorption. So physical adsorption, we have a weak vulnerable forces, and depends upon the nature of the gas or the adsorbate. Easily liquefiable gases are adsorbed readily. Heat of adsorption is small in this case, reversible in nature, forms multi-molecular layer on adsorbent surface, occurs at low temperature and decreases with increase in temperature. So physical adsorption, of course, we cannot have a high temperature. So as you know that if we increase the temperature, the kinetic energy of the molecules will be increased. So if we increase the temperature, kinetic energy will be increased. Hence, the molecules will not tend to retain on the surface and will leave the adsorption column. So here equilibrium is retained readily and is reversible. Whereas chemical adsorption, we will mostly discuss about the phenomena of the physical adsorption in our this topic of adsorption. So chemical adsorption, just for your understanding, that we have chemical bonds are formed, and ionic bond or covalent bond. Much more specific, depends upon the nature of both adsorbate and adsorbent. So that if they needs to react, then the reaction takes place at a certain condition. The molecules, their properties and their temperature and the pressure and the conditions. So very large heat of adsorption is released in this case, irreversible in nature, uh, forms unimolecular layer, takes place at high temperature, first increases and then starts decreasing with rise in temperature. So of course adsorption will be first, the adsorption rate will be increasing because the surface will be empty, and as the all surface is covered with the adsorbate, so then the adsorption rate will start decreasing. So equilibrium is attained slowly and is basically not reversible. So let us now discuss about the further details of the adsorption. So we have basically adsorbents basically are those solid particles that are being the column is prepared and their bed is prepared with that solid particles, and the gas or liquid is passed through them, and the unwanted material is being absorbed in that solid bed, and then the clean air is taken out. So we have basically four basic types of adsorbents. We have silica gel, we have molecular sieve zeolites, activated carbon, and activated alumina. So there are further definitions of two main definitions, concepts in the solid bed. Whenever we have solid bed, so one is the coverage is defined as a measure of the extent of adsorption of a species onto a surface. So it can also be defined in more ways, and usually denoted by the lower case Greek theta q. And exposure means a measure of the amount of gas which a surface has seen. More specifically, it is a product of pressure and time of the exposure. Normal unit is the Langmuir, where 1 L is equal to 10 minus 6 torr second. So let us move towards the principle of adsorption. Mostly things I have explained, but we will see what's the missing in this slide. So basically adsorption is a process which molecules of liquid or gas adhere to a solid surface. So we will focus exclusively on the gas adsorption. So adsorption is used for dehydration in addition to variety of air pollution control problems. So let us see certain applications of adsorption. So what we can perform with adsorption: removal of trace concentration of malodorous gases. Solvent recovery can be done, used in semiconductor industry, chemical industry. Meeting emissions requirement, typically adsorption is effective for any organic compound having molecular weight exceeding or equal to 45. Removal of trace quantities of hazardous air pollutants (HAPs) such as polyacrylic organic compounds, dioxins, furans, pesticides, phenolics, complex synthetic organics, removal of mercury vapors. So these are certain applications of adsorption that can be adsorption can be utilized to perform these tasks. So basically in adsorption we have two side by side columns, like column number 1, this is basically, and column number 2. So column number 1 is basically in the adsorption mode, like operational mode, and column number 2 is on the desorption mode, and it's basically regeneration. So here you can see we enter the dirty gas from the bottom, and operational cooler if you want to decrease the temperature of the gas. So this is basically a solid bed. This is a solid bed in which the solid particles are retained, that is basically adsorbents, so which I already discussed before, like silica gel, activated carbon, alumina, and so on. So dirty gas enter here, the unwanted material is retained on the surface of these particles, and the clean gas is recovered from the top. So this is basically absorption phenomena. And the second column, so once this column is saturated, the second column is utilized. This second column is saturated and is being regenerated by the using the steam, and with the steam the unwanted species that's retained already in the first column is being removed, and then condensed and removed organic liquid is separated here, and steam is converted into water and recycled to convert into steam. So when the first column is exhausted or is being utilized completely or saturated, it goes to the desorption mode, and the second column is in the adsorption mode. When second column is again utilized or saturated, it goes into a desorption mode, and first column is like again goes into the adsorption mode. So it's basically a fixed bed adsorption system mostly utilized. So there are certain disadvantages of adsorption, like for example the capacity of the adsorbent is limited, so we cannot deal higher flow rates in this. So capacity is limited, difficult to manufacture adsorbents with identical adsorptive properties, and it's basically slow operation, and it's more suited to the batch operation. So it's basically, these are certain disadvantages of the adsorption phenomena. So there are certain characteristics of the adsorbents which we required in order to have better adsorption rate. For example, the adsorbent should have higher internal surface area, should be porous, and the pores should be easily accessible, like the particle size must be smaller than the pore size, so particles can move through the pores and like surface pores and enter and retain inside the active sites in the pores. So being regenerate easily, do not age rapidly, like you can use it for 5 to 6 cycles, or at least 7 to 8 times cycles you can utilize it. So mechanically strong enough, that means if you have certain pressure coming in the feed stream or certain vibration, the particles should not break down further. So this is a typical molecular sieve of like a cubo-octahedral unit composed of silica and alumina tetrahedron. So this is basically the molecular structure of. So basically these are the structure of adsorbents into which the adsorbates goes and retain at the active sites. Uh, So actual phenomena. What is the actual phenomena? Most commercial applications used in particles, small particles of the adsorbents in a fixed bed. Fluid passes down through the bed. If it's liquid, it comes from top to bottom, and if it's gas, mostly gases enter from bottom and move upwards towards the top. So and components adsorb onto the solid. So first step is the solute diffuses through the fluid to an area near the solid particle. Then solute diffuses into the pores of the particles. Then solute diffuses to the pore wall, and then solute adsorbs to the pore wall surface. So this is the basic explanation of what is actually happening, how the molecules is basically an application of mass transfer and the law of diffusion. The molecules first travel from their bulk body and move towards the interface, and then from the interface they move towards the solid surface, and then from the solid surface they retain at the solid and then move towards inside the pore, and then retain at the pore wall surface. So the pore size remains important a part. So it's determined whether the compounds can retain by the given adsorbent molecules and are too large to fit into a given pore opening cannot be effectively absorbed. So as I told you before that the pore size like the molecules must be smaller than the pore size, so they can easily go through the pores and retain at the. If they are larger than the pore size, so they will not enter in the porous medium and then just retain on the surface, and then other molecules will move and leave the column as it is. So we cannot have good separation in that case. So molecular sieves are examples of adsorbents that are engineered to have well-defined pore size. For example, a molecular sieve of 3 angstrom and 3 angstrom pores will not emit the molecules larger than this. So molecular sieves are more often used to dehydrate gas streams, since can remove water vapors while not removing organics that are too big to be adsorbed. So let us move towards the adsorption equilibrium. What is basically adsorption equilibrium? So adsorption equilibrium are the basically curves, like graphs you can say, in which on the x-axis we have the C, which is equal to the adsorbate in solution over total volume. So it tells us about the concentration of adsorbate. Basically adsorbate is in the feed stream, like the dirty gas contains the adsorbate. So on the y-axis we have W, which is mass of adsorbate by mass of adsorbent. Now here you see the mass of adsorbent. Adsorbent is basically the solid particles of retained in the fixed bed. So their mass is usually fixed. So on the y-axis what is changing? Mass of adsorbate. So mass of adsorbate is changing. So we have a graph between C and W. So for example we have C, this is the value of C. So here how you read the graph, this is the value of C. Now you move towards the y-axis. First point we have this point, and in this case we will have this much y, and then we move towards the next line, and in this at this point we have this much y, and at this point in the third line in this graph we have this much y. I hope you understand. So when we fix the C, you can see one is this point, one is this point, and one is this point on the y-axis. So this figure is unfavorable. That means we have low adsorption here. So for the fixed concentration of adsorbate, we get less amount of adsorbate adsorbed in the adsorption column. Whereas this is a linear trend, this trend is the linear, like you can see is a straight line, and this line is the favorable curve. That means that we have higher mass adsorbate in the column for the given concentration of the adsorbate in the feed. So this is what we are after for the favorable curve. So we can have various cases in the adsorption. So we can have favorable curves, linear trends, that we'll discuss in the next lecture. So what's the dynamic adsorption? Dynamic adsorption basically the same phenomena, just the concept is like the molecules are moving and dynamic is happening dynamic like randomly or instantaneously. So adsorption for a control of indoor air contaminants. So there are basically many natural examples of adsorption which you see everyday life. For example, if you put salt in the room, after a certain time you can see the salt is becoming like it is becoming more have moisture inside it, and like uh, it is getting little bit wet. So what's doing? That's adsorption phenomena. So when you see that we have certain packets in the medicine boxes, that's basically silica gel. What's the purpose of that? To absorb the moisture from the atmosphere. That's also an adsorption phenomena. So this is everyday basically example. You can see the adsorption naturally occurring and spontaneously basically occurring, dynamic adsorption. So the physical and chemical properties of the adsorbent, including material composition, particle size, media thickness, and total surface area, pore volume. These all play the roles in the adsorption phenomena. Concentration of physical and chemical properties of the gases to be removed, concentration of the adsorbable gases, vapors, including water vapors, temperature of the ambient air. These all are the factors that affect the adsorption phenomena. Residence time of the adsorbate in the filter. So the gas filtration process of diffusion, mass transfer, physical absorption, desorption, and chemical reaction is a complex, but we can use several simplified models to predict dynamic and equilibrium behavior. So here you can see diffusion to adsorbent surface. These are the basically gas molecules, and this is the adsorbent. So you see the molecules are being moving inside the pores, and this is the monolayer buildup of adsorbate inside. So this show how the dynamically is moving and adsorption is taking place. So let us move towards the breakthrough curves. What are the breakthrough curves in the adsorption? uh, So adsorption is basically a transient process. What is mean of transient process is basically a changing process. That means like when you enter the feed into a column, the immediate entry point there will be certain condition. As you move down the bed, down the length of the bed or upward the bed, the conditions will be changing. So in the start, the adsorbents are saturated, then the phenomena move towards the next phase and then towards the next phase, and until it exits the column, the feed stream. I've explained further. The amount of material absorbed within the bed depends upon both on position and the time. So consider a time dependence. As fluid enters the bed, it comes in contact with the first few layers of the adsorbent. Solute adsorbs, filling up some of the available sites. So consider that you have just entered the feed into the column at time 0. Now adsorption started, and the feed stream is contacted with the first layer of the adsorption bed. So after certain time, like 10 minutes, 20 minutes, whatever time is set, that area will be saturated and adsorption will be moved further length of the bed, and then until it reaches the feed stream exits the column. So soon the adsorbent near the entrance is saturated and the fluid penetrates further into the bed before all the solute is removed. Thus the active region shifts through the bed as time goes on. This is the important point. So what's the break point? Break point is the fluid, as the fluid emerging from the bed will have little or no solute remaining, at least until the bulk of the bed becomes saturated. So that means at the start, for example, if time is equal to 0, and you have Ca naught, the initial concentration of the, let's say, the adsorbate, that's very high. So time is equal to 1, Ca1 concentration, that will be low, of course. So time is equal to 2, like 2, for example, 1 is 1 hour, 2 is 2 hour. Ca is equal to Ca2 and concentration is low, and then time is certain, let's say time is any n value. So now Ca will be equal to Ca naught. That means now the adsorption, uh, how much adsorption takes place, it's completely saturated, and now again the exit stream having the same concentration of the entering stream. So this is basically a break point where when the concentration of the fluid leaving the bed spikes as unadsorbed solute begins to emerge. ठीक है जी, इसको मैं इस तरह समझाता हूँ कि आप टाइम स्टार्ट 0 पे करेंगे और जो फीड है वो एंटर करेंगे एड्जॉर्प्शन कॉलम के अंदर, और जिस तरह एड्जॉर्प्शन कॉलम में आपके पास एड्जॉर्प्शन होती जाएगी, कॉलम आपका सैचुरेट होता जाएगा। जब बाहर आपकी कॉन्सेंट्रेशन दोबारा वही हो जाए जो शुरू में एंटर कर रहे हैं आप, दैट मीन्स कि आप कॉलम में मजीद एड्जॉर्प्शन नहीं हो रही, तो ये आ जाता है आपके पास ब्रेक पॉइंट। तो इस पॉइंट पे आपके पास आ जाता है द ब्रेक पॉइंट हैज कम एंड द कॉलम हैज बिकम इनफेक्टिव। इस केस में आपके पास जो बेड है और कॉलम जो है वो आपका इनफेक्टिव हो गया, तो आपको उस कॉलम को अब स्टॉप करके रीजनरेशन पे लगा देना चाहिए और दूसरे कॉलम को आपने अंडर ऑपरेशन आपने यूज कर लेना है। So break point composition is said to be maximum amount of solute that can be acceptably lost. So typically something between 1 to 5%. So आपने उसको 100% पे नहीं जाने देना, आपने उसको Tn से पहले ही let's say 9 या 10 पे ही स्टॉप कर देना, ताकि जो आपकी कॉन्सेंट्रेशन बढ़ना शुरू हो रही है अब, because you will measure the samples after every certain time intervals. So जहाँ पे कॉन्सेंट्रेशन बढ़ना शुरू होगी वहीं पे आपने उसको एटलीस्ट 1 to 5% पे मार्जिन रख के, यानी आपने उसको स्टॉप कर लेना, क्योंकि ज़रूरी नहीं कि आपके पास डर्टी गैसेज ही हों, आपके पास उसमें प्रीशियस मेटल्स भी हो सकते हैं जो आप रिकवर कर रहे हैं, प्रीशियस सब्सटेंसेस भी हो सकती हैं, तो दैट कैन नॉट बी लॉस्ट। So this is also another curve. On the x-axis we have height of bed. Height of bed means this is the length, bed length, and this is C by Ca naught. You know, C naught will be fixed. That's the entering concentrations at time 0, and C will be changing. So at start time 0, C will be equal to C naught. This is basically 1. So C will be decreasing, of course, and after certain time these curves will be formed. C will be decreasing, and this curve could be like this one, this also certain also this trend. So mostly it follows this trend. So this is basically how the saturation moved through the bed. So here you can see this is now the column, we have column taken in the horizontal direction for your understanding. This is the horizontal direction, and for example this is the feed entering and this is the feed, like the inlet gas which we need to purify, and this is the concentration. Now this is the saturated zone, where this is basically adsorption zone and this is fresh zone. So the saturation moved down the bed. So actual adsorption is taking place in this column. Here you can see we have constant value and this is a decreasing trend here. This is basically adsorption taking place in this column. So here you can see another slide, adsorption zone. adsorption zone, inlet gas flow, and inlet gas flow, and this is the inlet gas flow C naught. This is basically a saturated zone. This is a vertical. This is an adsorption zone, and this is the clean adsorbent bed. So this is the outflow. So this you can see certain times T1, T2, T3. This is the concept of breakthrough time. So you can see on the x-axis we have time of operation. On the y-axis we have concentration. So at the start, uh, outlet concentration, you can see this is the inlet concentration, this is the effluent standard. Inlet concentration is C naught. So this is outlet concentration time T1, the concentration is very low, like that means absorption is going on very good. So at time 3 T3, as the column is being saturated, you see that the concentration now is certainly increasing, spiking. So at this point, this is the break point, 1 to 5% of the like total concentration, where you have to stop the column, so the adsorbate should not be lost. So this is the breakthrough curve, and this is the TB time, sorry, breakthrough time. And so these are the points you can read, which I have explained, just for you to read again. As a concentration wave moves through the bed, most of the mass transfer is occurring in a fairly small region. This mass transfer zone moves down the bed until its breakthrough. The shape of the mass transfer zone, as I told you, it could have different shape, depends upon the adsorption isotherms, equilibrium expression, flow rate, and diffusion characteristics. So shape must be determined experimentally, and it's determined experimentally because you are taking the samples after certain time, and the values, the readings, like on the base of the readings, the graph trend is formed. जिस तरह की आपका values आएंगी उसके अंदर readings के experiments के results के बाद, उससे ही graph बनेगा ना, उस graph का फिर trend आप जो है ना वो different हो सकता है different cases के साथ. So adsorption zone, this is I think the points I already discussed. So just downstream of the saturated zone, there is a region partially in equilibrium with the adsorbate. So this region contains a concentration gradient and is referred to as the mass transfer zone or adsorption zone. So as time progresses, the adsorption zone moves deeper into the system and eventually approaches the exit from the bed. When the adsorption zone has moved through the filter, the concentration of the outlet air will be the same as that of the inlet. This process is described by the breakthrough curve. The time-dependent concentration of the pollutant at the outlet from the bed is shown before. So what is the breakthrough curve? The breakthrough curve is the time elapsed from the start of filtration until the effluent concentration has reached a maximum permissible concentration Cs, which is a value acceptable from a toxicological or other user point of view. So the breakthrough time of a specific adsorbate system includes the useful life of the filter for control of that contaminant. The breakthrough capacity is the amount of the gas or vapor adsorbed by the filter expressed per mass of the adsorbent when the breakthrough time is reached. So ये वही बातें हैं जो मैंने आपको सारी फिगर के अंदर समझाई हैं कि ब्रेक थ्रू टाइम क्या होता है. अब आपको पता होना चाहिए एब्जॉर्प्शन जोन क्या है, ब्रेक थ्रू टाइम क्या है, ब्रेक थ्रू कर्व्स क्या है. तो अगर ब्रेक थ्रू टाइम आपने निकालना हो तो दिस इज अ रिलेशन फ्रॉम योर बुक, basically where mb is equal to integration 0 to time tb c initial minus c exit q into dt. इधर qo जो है वॉल्यूमेट्रिक फ्लो रेट है, mb is the adsorption capacity, maximum mass of adsorbed species per mass of the adsorbent. And if you need to further integrate this, and you can see that अगर उसी रिलेशन को फर्दर इंटीग्रेट करें तो आपके पास ये रिलेशन बन जाएगा TB is equal to WE over CIQ W minus rho B Q over K and ln CI over CE. So here TB is the breakthrough time, C is the exit concentration, CI is the initial concentration, Q is the volumetric flow rate, W is the weight of adsorbent, rho B is the bulk density of packed bed, Kn is the rate coefficient, W is adsorption capacity. ये कुछ constants values हैं. सो टी बी और डब्ल्यू की तरह ग्राफ प्लॉट करेंगे आप, तो आपके पास रेट कोफिशिएंट और एब्जॉर्प्शन कैपेसिटी की वैल्यू आ जाएगी इंटरसेप्ट और स्लोप से। सो डिफरेंट एड्सॉर्बेंट्स आप देख सकते हैं, जो कि ये आपकी बुक से ही टेबल है, जिसमें सिलिका जेल है, एड्सॉर्प्शन एक्टिवेटेड एल्यूमिना है, कार्बन्स हैं, जियोलाइट्स हैं, पॉलीमर एंड रेजिन्स हैं, क्ले एसिड्स ट्रीटेड एंड पिलर्ड हैं। तो इसमें डिफरेंट एप्लीकेशंस हैं, मैं कुछ आपके लिए, जैसे ड्राइंग ऑफ गैसेस और रिमूवल ऑफ HCl फ्रॉम हाइड्रोजन एक्टिवेटेड एल्यूमिना के लिए यूज होता है। नाइट्रोजन फ्रॉम एयर को रिमूव करना है तो कार्बन्स, इथीन फ्रॉम मीथेन एंड हाइड्रोजन, रिकवरी ऑफ सॉल्वेंट, रिमूवल ऑफ सॉक्स एंड नॉक्स। सो आप देख सकते हैं वेरियस बहुत ज़्यादा एप्लीकेशंस हैं जो आप गैसेस को रिमूव करवाने के लिए, तो एड्सॉर्प्शन आप क्राइटेरिया यूज कर सकते हैं। सो क्लास, थैंक यू वेरी मच। आज हमने डिस्कस किया एड्सॉर्प्शन के हवाले से। अब आपको एड्सॉर्प्शन की बेसिक डेफिनेशन, उसकी एक्सप्लेनेशन, उसका एक्चुअल फिनोमिना, फिर उसका जो कर्व्स हैं, इक्विलिब्रियम कर्व्स हैं, वो हम नेक्स्ट लेक्चर में, सेकंड लेक्चर में मजीद भी डिस्कस करेंगे। सो एड्सॉर्प्शन बेसिकली, इसमें भी एक कंटेनर होता है, एक कॉलम होता है, उसके अंदर आपके पास एक एड्सॉर्बेंट्स होते हैं जो के अंदर सॉलिड पार्टिकल्स होते हैं, और नीचे से गैस आती है, यूजुअली जो आप कह लें कि डर्टी गैस है, उसमें से आपने एक अनवांटेड चीज़ को रिमूव करवाना है और क्लीन गैस को जो है ना वो बाहर थ्रो करवा देना। सो इसमें आपने पार्टिकल साइज, पार्टिकल डिजाइनिंग के अंदर जो बेसिक स्टेप्स हैं, उसमें आप पार्टिकल साइज, पार्टिकल्स पहले चूज करते हैं कि एड्सॉर्बेंट कौन सा होगा, उसका साइज क्या होगा उनके, फिर आपके पास वो उनका वेट क्या होगा, उनकी ओवरऑल जो कॉलम ऑफ डायामीटर का जो, सॉरी, कॉलम का डायामीटर जो है, और उसके अलावा फ्लो रेट्स आप सेट करते हैं, और कॉलम की लेंथ और हाइट, और जो फिर आप ओवरऑल डिज़ाइन ब्रेक थ्रू टाइम बताते हैं। ये आपके पास जो है ना इसमें फर्दर डिजाइनिंग स्टेप्स होते हैं, जो कि आप फिर इक्विलिब्रियम कर्व्स के जरिए जो है ना वो फाइंड आउट करते हैं। So thank you, and if you have any question, you can just email me or WhatsApp me or contact me in person. Thank you very much.